Yesterday you guys started working on this lab. I'm not sure how far you got, but I wanted to run through a couple things real quick and see what we got. Okay, so this is just an introduction, right? This is what a sound level looks like versus time, and over here it says sound level in volts. Basically the microphone is responding to the vibration of the air, and it changes the resistance value of this little diaphragm. Anyways, it's measuring pressure differences. So we've got high pressure, low pressure, high pressure, low pressure. That corresponds with the sound wave being produced, a compression and a rarefaction. Okay. Now, pre-lab question: given that a sound wave consists of pressure increases and decreases, what would happen if one increase was at the same spot as another decrease? Well, they should cancel each other out, right? Something's trying to squish something together at the same time another thing's trying to pull it apart. It should be canceled, no effect. Okay. Well, we want to test that. We want to see what happens. Okay, so we actually used two tuning forks today and the microphone to measure these waves, and we did it individually and then together. Okay, and so I have some of this data here. Let me go ahead and pull it up. Okay, the waveform for one of the tuning forks looks like this, and you can see it's a sine wave, right? And so if we do an analysis of this, if we say, okay, well, let's just see what its frequency is or what its period is. If I drag from the high point of one wave to the high point of another wave several crests later, okay, and so I've got 1, 2, 3, 4, 5, 6, 7, 8 cycles in here. 8 cycles in 0.25 or 0.025 seconds. That allows me to go ahead and get the frequency and period for this. Okay, so at 8 cycles, it was like an 8 cycles in 0.0251 seconds, and of course cycles per second, 8 divided by 0.0251 would get me its frequency, and that's in hertz, and then the period would be the inverse of frequency. Okay, repeated the process for another wave. Now this one that I just did, okay, how does it compare to the stamped frequency? Well, when I did it in class, it was really close. In fact, there was one of them that was right on. So I expect these to be fairly close to the frequency that's stamped on the box. Mine says 318, and I believe it was supposed to be 320. Okay, so remember, a percent difference would be something like 318 minus the 320 it's supposed to be divided by the 320 it's supposed to be, absolute value, and then multiply it by 100%, make it a percent. Okay, I'm guessing it's fairly close, less than a 2% thing, so whatever. Okay, I did collect for another tuning fork as well, so I'm going to cancel out of this analysis, and so run 2 was a different tuning fork, and you can see this wave is a little bit longer, it's not as frequent, and if we analyze this one with the delta, then I can drag from a high to a high, crest to crest, okay, and I see 1, 2, 3, 4, 5, 6, 7 cycles in 0.0273 seconds. Okay, 7 in 0.0273. And again, I can take 7 divided by 0.0273 and get my frequency, and I think this one should be close to 256. So let me check the math there. 7 divided by 0.0273, and I get 256.4. Okay, so again, that's pretty close to exactly what I wanted, 256 hertz. Again, really good numbers. Now the question here is, what would happen if we put these two waves together? Okay, so I want to show you both waves at the same time, and I'll get these displayed so that we can look at both of them at once. Okay, so here we see both graphs at the same time, and I'm going to superimpose them. I'm going to put them right on top of each other in a minute, but you can see This red one at the top happens a little bit more frequently, this blue one at the bottom a little bit less frequently, but they're both oscillations that go up and down in time. Now I'm going to go ahead, I'm going to superimpose these onto the same graph. With both of these on the same graph, you can see a little bit more clearly what happens. Like right at the beginning, this green line and this red line, they're complete opposites of each other. And so I've got a peak up here and a peak up here. And then as time goes by, they get closer and closer to in line with each other until you can see right here, they line up almost exactly. And then they start to misalign again. And then in here, we see that they misalign almost exactly, but then by the time we get over here, they're lining back up again. Okay, so this was two waves recorded at two different times. What happens if we play the tuning forks together and measure the resulting wave? When we do that, we get this graph. Okay, this graph shows two patterns. It shows a sine wave inside a sine wave. Okay, so you've got a quick vibration, but then you've also got this bigger vibration where you have this peak and valley, peak and valley, peak and valley. Okay, and so this is what happens when two waves interfere. They move through each other, and when they're going in the same direction, they add together and get bigger. When they're vibrating in opposite directions, they add together and get smaller. Okay, so if I go ahead and I superimpose one more time all three graphs together, okay, you got to kind of pay attention to what you're looking at. And these didn't necessarily start at the same time. In fact, I see that they did not. So yeah, that's a mess. So let's look at this a different way. Okay, I'm going to bring in a wave simulator, and we've looked at this before. Okay, and so I'm going to have an end on this one so that I actually get a reflection that comes back. And I'm going to change it to pulse. I'm going to turn damping down, and I'm going to send two pulses. Then I'm going to pause it. Now, this wave is going to get to the end and it's going to start to come back. And so I'm going to step this through. Okay, so that wave got to the end and now it's reflecting back on the other side. So now this wave at the bottom is coming back to the left. This wave is at the top is moving towards the right, and they're about to hit. So let's see what happens when I step through. Okay, it looks like there's no waves anymore. It looks like they cancel each other out. So those two waves got together and got smaller. Okay, well, but then they keep moving. Okay, so this is the wave that was on the bottom and it's coming back to the left. It's still on the bottom, still coming back to the left. This wave that was at the top right is still going over there, and so now both waves are coming back. Okay, now what if I've got two waves that are going to go in the same direction? So I'm going to change this end to a loose end, which changes how it reflects. Pulse, pulse, and again pause and play. Now this one, instead of reflecting back on the bottom, is going to reflect back on the top. So now they're coming together. Okay, but they're both on the top now, so they're both vibrating in the same direction. If I step through this, and those two waves hit, and they make one really, really big wave, and then they move through each other, and then I'm back to having one small wave again, or two small waves. Okay, so I can play this back and forth, and we can see sometimes they add up and interfere constructively, and sometimes they add up and interfere destructively, which is exactly what happens when you play two tuning forks at different frequencies. Sometimes they add up and interfere constructively, and sometimes they add up and interfere destructively. Okay, and so the beat frequency, the last part of this lab, is to go through and say, well, how many beats did we get? Okay, so I'm going to pull up this lab again, and I'm just going to go run 4, which was my single beat frequency. And if I'm going to do the analysis on this one, okay, I'm going to do the delta, and I'm going to go from peak to peak, but it's going to be the major peak. So here's one major peak, and then there's another, there's another, there's another, there's another. So I'm going to go from here to here, and I'm not counting all the waves in between. I'm just counting the bigger outside wave. Okay, so this is what's called beats when they misalign and align. So I've got 1, 2, 3, 4 4 beats in 0.0626 seconds. Okay, so my number of cycles over here is 4, and my time, I have a delta t, so I don't have to do the beginning and end. I'm just going to give a delta t of 0.0626, 0.0626. So the beat in seconds, that's really the period for this thing. Okay, I'm just going to go ahead and get the frequency. That's really what I'm interested in. 4 cycles divided by 0.0626 seconds. 4 divided by 0.0626 is about 64. Okay, give or take a little bit. How does the beat frequency appear to be related to the frequency of the tuning forks that made them? Well, I had a 256, okay, for one of them, and I got to scroll back and look to see what my other one was. The other one was 320, I think. 0.8 divided by 2.025, yeah, 320, okay, or 318, so close enough. 256 to 320, well, that's 44 to get to 300, and then 20 more is 64. The difference between these two frequencies is the beat frequency. Okay, that's how many times they align and misalign per second. Okay, they align and misalign 64 times. So test your prediction by measuring the beat frequency of another combination. You don't have to do that since the tuning forks are only on the one box. You can't really do that. The beats occur because of wave interference. Okay, wave interference. Sometimes they add up and get bigger, sometimes they add up and get smaller. When two waves interfere, what are the possible results? Well, just like I said, we could either get a bigger wave or smaller. Okay, they can either help each other out or they can cancel each other out. But after interfering, they keep going. They continue, which is interesting because usually, you think of two things smashing into each other, they don't get to just keep going afterwards. But a wave is not matter. A wave is the transfer of energy. So it can actually have two waves in the same spot at the same time. They interfere with each other and then they move past each other. Okay? Hopefully this lab made sense. There's one more thing we're going to look at today. It's another lab. We want to look at what happens when waves reflect off of one surface and hit another, and then there might be a quiz tomorrow on some wave behaviors. So it might be a good idea to review this content in the book. I will get you guys the lab sheets today.